Hello guys and welcome back to the Physics and Maths blog. Today we're going to go over binary operations. This is the 5th video in our Abstract Algebra series. I hope you guys are enjoying this series. So let's just get straight into it. So what is a binary operation? So by definition, a binary operation star, for example, on a set S is a function mapping S and S into S. So for each A and B in this joint set thing, we will denote the element star of AB of S by A star B. So that's quite confusing, but essentially what it means is the same. It's taking two elements, A and B, from the set S. So one from A from set S and a B from set S. Well, that's where the S cross X is, and then combining them to form one element, which is also in the set S. So essentially a binary operation is taking two elements, put them together to make one. That's what you should think a binary operation is. So example, our usual addition plus is a binary operation on the set R, real numbers. However, our usual multiplication, which is our dot, is a different binary operation, but it's still in the same set R. So 2 plus 2, that's a bad example, 2 plus 3, our usual binary operation gives you 5, which is also in the real numbers. But if we use the binary operation of multiplication, we have 2.3, which gives you 6, which is also in real numbers, so they both exist in the same set, but they are completely different operations. Binary operations, that is. So, binary operations and subsets. We've mentioned subsets before in our first video, and we applied them in our second question video. So, let star be a binary operation on S, and let H be a subset of our set S. The subset H is closed under our binary operation if for all A and B inside our H subset, we also have the binary operation being inside that H subset. In this case, the binary operation on H, given by restricting the binary operation to H, is called the induced operation of the binary operation on H. So essentially, if we have a big set S and we have A and B inside S, and they form to make another SC, for example, in the set, if all of them exist in the subset of H, then H is also, the binary operation works inside the induced subset of the big set, which is H. So an example of this, our usual addition on the set of real numbers does not include a binary operation, is not the same as a binary operation on the set of R star, which is the non-zero real numbers, so the real numbers just without 0. This is because 2 exists in R star, the real number star, and minus 2 also does. But if we do the binary operation of addition on them, we get 0, which is not in the non-zero real numbers. And so R star is not closed under our binary operation. There's quite a few stars there. I probably should use a different notation, but you get the gist. So the next two things will be important later in the series. They're quite good definitions. So we have commutative and associative binary operations. So a binary operation on a set S is commutative if and only if A star B is the same as B star A for all A and B in the set. So this kind of relates to the symmetric value that we saw in equivalence relations, how it has to work one way. If it works the other, then it's commutative. And then for associativity, we have a binary operation star on a set S is associative if A star B in brackets star C is the same as A star BC for all A, B, and C in the set. So that just means it doesn't really matter which way you do it. If you get the same result, then the binary operation is associative. A good example of an associative and commutative binary operation is multiplication, because it doesn't matter which way you multiply things together, which ones you do first, you'll end up getting the same product. A theorem on associativity and of composition. So let's say we know what composition is with two functions or three functions. So let S be a set, and let F, G, and H be functions mapping S to S. So we have our functions there. Then F composite of G composite H is equal to F composite of G composite of H. The proof here is, as you can see on screen, I'm not going to read it all out, but essentially it breaks it down into little segments. If you want to pause and have a read, that is the whole proof. That's all you need. It's quite short, but it does prove it because you do end up getting the same element in the end of F, G, H of X, which is in S, which is proven. Tables. So this is something that personally I've not really used that much, but is quite useful if you want to see it a bit more visually for binary operation. So if you have a finite set of binary operations on a set, then you can put it into a map to see how the rows and columns match together and gives you your answers in the middle part. So let's say we have binary operation on S to S of A, B, and C. As you see, we've made a table here with our binary operation in the left-hand corner. We have ABC across the top and ABC down the sides of our rows and columns heads. And then we can see what happens when A star A happens, we get B. B star B, we happen to get C. And you can see all our values together. However, this is actually quite useful, this table, because we can see that A star B equals C, but B star A equals A. And so we can see that the binary operation star is not commutative for this personal example. So it's quite a good way of visualizing it if it is commutative, associative, whatever. Quite a good way to do it is using a table. Anyway, thank you guys for watching. Make sure you hit like, subscribe. Carry on following this series if you're interested in abstract algebra for more content, examples and proof. And I'll see you guys in the next video. Goodbye.